Hi, and welcome to the first two videos on the binomial expansion from the year 2 of the course. And what we're going to do is build on the work that you did last year on binomial expansion when we just looked at expansions for natural values of n, the power. So we're going to extend that to look at what happens when n is rational, and I'll talk a little bit about what I mean by rational in a second. And then we've got to understand that these expansions, as we go further into it, are only valid for certain values of x within the expansion. And then finally, there's a section on how we can use particular values of x as approximations, and also the last bit at the end is how we deal with things that are a lot more complex. So there's quite a bit to get through. We're going to do it in two videos. The first video, I'm just going to look essentially at those first three bits there, and then in the second video we'll look at a bit that's greyed out, which is to do with values for in this expansion where this value here, a, is not equal to 1. Okay, so let's crack on, and the first thing we're going to do is just remind ourselves about binomial expansion from year 1, when n is a natural number, and the natural numbers are just the values, essentially the counting numbers from 1, 2, 3, 4, 5, 6 and so on. So what we've got here, this little notation here says n belongs to the natural numbers, and we've got that mess of stuff, and let's just unpick all of that. So what we've got is our binomial coefficient in each term. Then you've got descending powers of the first value, in this case a, and then you've got ascending powers of the second value, which is b. So again, there it is again, NC1, our binomial coefficient, descending powers of a, ascending powers of b, and so on and so forth, all the way through to the end, where we've got a to the power 1, b to the n minus 1, so we've now nearly used up all our a's, but we've got a load of b's sitting in that term. And then there at the end, there it is, a to the power of 0, b to the power of n. So that's our general definition, which is important so we can describe what's going on, but as with a lot of things mathematically related, it's always a lot easier to see what's happening when we do an actual example. So let's have a look at this one. We've got 2 minus 3x to the power 4, and so when I do the expansion of that, that's what I end up with. So let's just have a quick look at it term by term. So we've got first term 4c 0, 2 to the power 4 minus 3x to the power 0. We should know that that bit there is going to be 1, that bit there is going to be 1, so there's no real need for those two terms, but I like to put them in just for the sake of completeness and structure. Let's have a quick look at my second term. They go 4c1, 2 to the power 3, so we've got descending powers of 2 minus 3x to the power 1, ascending powers of that thing. And again, I'm making sure I've got my brackets here because that helps me get around sign errors. So for example, in this term here, it helps me think about the fact that I've got minus 3x squared, which would actually be positive 9x squared when we get to it, and so on and so forth for the last two terms. So just take a moment to make sure you're happy and comfortable with all of that. And then when we start number crunching on the calculator and splitting out the values, what we end up with is our expansion that looks like that. And again, you'll notice that it's important we're being careful with signs, because in this particular case we've got alternating positive and negative signs for each of our terms. And it's worth noting that a lot of times you might end up with kind of terms getting repeated. That is just entirely coincidental. There's no particular reason for why that's happening. And you sometimes see that happening within your expansions. Okay, so that's a recap of what we've done where n is natural. So what we're going to do now is extend this to include expansions where n is rational. So that's this bit here, n belonging to this kind of q thing here means rational. And what that means is that our value for n, our power, n, rather than just being a number, 1, 2, 3, 4, 5, 6, or whatever it is now either negative or fractional. And that kicks up a whole bunch of issues. The first is what you get is an expansion that's got an infinite number of terms. This one has got a finite number of terms. There's a limited fixed number of terms, in this case 5. But when we get negative or fractions involved, then we get infinite expansions, and there are good reasons for that. And so what we're looking at is doing this kind of expansion here. So where this one is where I've got a negative value, and this one here where my power is fractional. Okay, so those are the kind of things we're going to go at now. Right, so there's some basic ideas that I'm going to talk about, and there's very sound mathematical principles behind those, and if you want to research them a little bit more, please feel free. But for now, I'm just going to make sure that we go through them and describe them, rather than going into mass amounts of details on them. The first is, one I've already mentioned, is that what you get from these expansions is an infinite number of terms. So these things go on forever. And what that means is, because it's not possible to write them all down, because, as I said, there's an infinite number, that means that our expansion essentially becomes an approximation, not an exact value. And that's important to understand. Having said that, the more terms we include in our expansion, the more accurate it's going to be as an approximation. The next point is that this expansion is only going to be valid for certain values of x. It doesn't work for absolutely everything. And then the final point is that definition of, or the concept of factorial, which is in there within our expansion that we saw previously, works slightly different. You can't have a factorial of a negative value or a fractional value, so you can't have, for example, 4c minus 3. It just doesn't exist. So what we've got to do is redefine how we describe the binomial coefficient. So what we're going to do is have a quick look at that now and look at that reworking of it. So here we go. So if we take the terms from Pascal's triangle, they all come out as being that. So this combinations definition is NCR is n factorial over r factorial n minus r factorial. Remember, factorial being, for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. So if we had 5c3, that would be 5 factorial over 3 factorial, 5 minus 3 factorial. This bit here clearly being 5 minus 3 being 2. And if we wrote those out, we've got 5 times 4 times 3 times 2 times 1 on the top, 3 times 2 times 1 times by 2 times 1 on the bottom. And you can see straight away there's some cancelling that can happen. So I'm going to get rid of those bits. And that leaves me with 5 times 4 on the top, divided by 2 on the bottom, and that's how we'd actually physically go about calculating that value. Now, if we have a look at what that means, and if we do that exact same principle just in terms of n and look at it for our first few terms of our expansion, NC0, now this is a very bizarre thing, 0 factorial. As it turns out, 0 factorial actually equals 1. And you can go and have a look on the internet for all the raging arguments about that particular one and why that works. But for now, just take it as at face value that 0 factorial actually has a value of 1. N minus 0, that's just become n's factorial. So we've got n factorial over n factorial, so that's just got a value of 1. Right. NC1 is that. So we've got n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to finish off with 2 times 1. And so on the bottom, we've got n minus 1 factorial, which starts off at n minus 1, n minus 2, n minus 3 times n minus 4 times n minus 5, blah, 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 all the way down to 2 times 1. And so what we can see is all of that bit on the top there will cancel against all of that on the bottom there, and that just leaves us with the value of n. So NC1 is always just n. So for example, if we think about Pascal's triangle, the first value on, let's say, the fifth row would be 1. The second value, 5C1, is 5. So it's the same as the row number, and that happens on any row. So that's something kind of we already knew about. If we take NC2, which is that thing, n factorial over 2 factorial, n minus 2 factorial, do the same as before, and then think about where the cancelling happens. The cancelling is going to happen there. So that leaves us with n minus 1 over 2 times 1. And then we'll finally do NC3, same ideas, do the cancelling. There we go, and we end up with n minus 1, n minus 2 over 3 times 2 times 1. What all that means is, if I just get rid of a lot of stuff and bring it all together, we've got our first value is 1, NC1 is n, NC2 is n minus 1 over 2 factorial, NC3 is n minus 1, n minus 2 over 3 factorial. And what we're going to do on our expansion now is work with particularly these definitions here, rather than this kind of definition up here. Okay, so that's a lot of the basics behind what's going on. The other thing we've got to deal with is having a value of a, this first value here in our bracket, that's not equal to 1. That causes a world of issues as well, so we're going to have to do a bit of manipulating to be able to deal with that one, but we'll deal with that in the second video. Right, that's a lot of talk, a lot of chat. It's important stuff, but now we're going to get on to how we go about dealing with these things in practice. So, here we go. What that means is the expansion of 1 plus ax to the power n, where n is rational, is that thing there. So we've got our first value is always going to be a 1. Our binomial coefficient we saw for the first term, NC1 is just n. NC2, there's that. NC3. And NC4, we just keep that going. So NC4 will be n minus 1, n minus 2, n minus 3, all divided by 4 factorial. And we just keep going and keep going and keep going. It's an infinite series, so it just goes on and on and on forever. Now, let's have a look at an example. So we want the first 4 terms of the expansion of 1 plus x all to the power half. So we've got this rational power. So here we go. 1 plus x to the power half. So first term is 1. Second term is n times by ax. So n is half. times by ax, in this case is just 1x, which is just x. For the next one, we're looking at this term here. So this bit here is going to be n, which is half, times by half minus 1, which is a minus half. 2, that's our 2 factorial, and there's the ax squared. And then the next term is going to be half minus half, take off another 1, we've got minus 3 over 2, and we've got 3 factorial on the bottom there, and there's our ax cubed. You'll notice that we wanted the first 4 terms, but that only goes up to the cube term, the power 3 term, because the first term is the x power 0 term, which is just 1. So we've got 4 terms there, and now all we've got to do is a bit of tidying up. And again, we've got to be careful with signs, so let's just tidy that up. So we've got 1 plus half x. This bit here, half times by minus half, all divided by 2. And notice we've got a negative in here now because of the negative there. On this one, we've got a minus times a minus there, so that's going to turn it back into a positive. And there we go. There's our expansion of first 4 terms, and the little note there saying we've got to be very careful with signs. So there it is. There's our first four terms of our expansion of essentially the square root of 1 plus x. Now, we're saying that 1 plus x to the power half is the same as that. Let's now have a look at what that looks graphically and get a sense of what's happening in terms of values for which this expansion is valid. So, that's my graph of the square root of 1 plus x, or 1 plus x to the power half. That's what it looks like. And so what I'm going to do now is overlay that with terms coming from here, but I'm going to use increasing number of terms. I'm going to start off with just the line 1 plus half x, just that part of our expansion there. Okay, there it is. And you can see our blue line is a pretty good approximation to our red line when it's close to 0 for just that section there. So you can see why we're now saying that's an approximation. But as we go away from those values, if we get further away from x equals 0, you can see that the blue line diverges from the red line. The blue line down here diverges from the red line. So it's reasonable to begin with, just for a small number of terms. Now let's have a look at what happens if I use 3 terms. So we've gone away from a straight line. The first 2 terms is linear. Now we've got essentially what's a quadratic approximation, and it's curved. And that curve is giving us a slightly better approximation, and it's doing it for values that are a little bit further away from 0. And if we go for 3 terms now, there we go. So what we've got is a cubic. And again, the bend of our cubic is again fitting better to our red line here. So what we can see is that adding additional terms, each time the more terms we include, the more accurate our approximation gets, which is something we mentioned previously. And what I'm going to do now is just, there's the power 4, so if I included an extra term there, and there's the power 5, and it's getting better and better. But what you'll notice is that it doesn't matter how many terms we include, at some point these curves are always going to diverge. So you'll notice for the power, when we had the power 4, it was a kind of U-shaped curve, so it went away from the red curve. Here it's a power 5, that kind of S shape, but again here it's diverging away from our red line. And the same is happening down here. So what that tells us is that these expansions, no matter how many terms we include, power 6, power 7, power and so on, these things are still going to diverge beyond a certain point. And what we're saying is that these values are only valid for mod x less than 0. And there's a mathematical reason for that, which is linked to, if you have done any work on geometric progressions, you'll see the same restriction existing within those. So it's linked to that. So what we're saying is that this expansion is only valid for values of x between 1 and minus 1, or mod x less than 1. What that generally tells us is that if an expansion is valid for mod x less than 1, for an expansion where we've got a value of a here, for example up here our value of a is 1, but if we've got, for example, this was 1 plus, I don't know, 2x or 1 plus 3x to the power n or whatever it is, then it's valid for mod ax less than 1. So that just principle there, it just extends for values where we've got an x coefficient. Right, let's put all that together and have a look at an example where we've got to come up with values for which the expansion is valid, and then look at how we can use that for making an approximation. So here we go. We want the first 3 terms of that expansion there. So our first term is going to be a 1, always is. Our second term is n, which is 3 over 2 times by ax. Our next term is that n minus 1 over 2 factorial times by ax squared. And it says we want the first three terms. 1, 2, 3 terms. There you go. I don't need to go any further than that. Now let's do some tidying up. So we've got 3 over 2 times by minus 4, minus 6. And here we've got 3 over 2 times by half, divided by 2, times by minus 4 squared. Put it all together, and we've got, that gives us plus 6x squared. And I mentioned this previously, but the fact that we've got the coefficient for two subsequent terms the same is just a coincidence. All is a coincidence. Right, so there you go. There's my expansion, the first three terms. There we go, part A done. So part B says, state the range of values for which the expansion is valid. So we know from the previous slide, we're saying that our expansion is valid for mod 4x less than 1. So what that means is, if we just do a bit of dividing, that gives us mod x less than a quarter. So basically what we're saying is that this expansion will give us a reasonable approximation if we've got values of x between positive a quarter and negative 1/4. Now it says here we're going to take a value of x to be 0.01, which is valid. It's certainly within that restriction there, so that's okay. I'm going to find an approximation from root 6. So here we go. So we're going to let x equal 0.01. And if we take that thing there, which is our original expression, put in 0.01 as our value for x, that leaves us with 0.96 at 1 minus essentially 4/100ths. And then if we do a bit of square rooting and cubing of that, what we end up with is that, so 96 over 100 square rooted becomes 2 root 6 over 5. And then cube it again, and what we end up with is 48 root 6 over 125. Now, what we're going to do is use that value, but we're going to do essentially the same principle again, using x equals 0.01, but this time we're going to put it into our expansion. So before we put it into here, now we're going to put it into this thing. So let's put our value of 0.01 into there. And so that gives us a decimal value of 0.9406. And because we've done that thing in two ways, we know that those two things have got to be approximately equal. So when we put our value of 0.01 into here, we got the 48 root 6 over 125. Put it into our expansion, we got that. So therefore those two things are slightly equal, or approximately equal. And we want an approximation for root 6. And there's the root 6 sitting in there. So what we've got to do now essentially is just rearrange this to make it say root 6 equals. And that's a fairly straightforward job of just doing times by 125, divide by 48. And there we go. We've got an approximation for the value of root 6, which is 2.449479, blah, 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 and on it goes. The second part of the question is, so, well, how accurate is that as a value for the square root of 6? So let's have a look at our percentage error. So the percentage error, the top bit is the difference between the actual value and our approximation. So again, if it was me, I'd be doing this, and I've got this value off my calculator. I'd keep that on the calculator, then just use the A and S key to put those values in. So divide that by the actual value itself. So we're doing the difference divided by the actual. How far away is that? As it turns out, it's very, very close indeed. So what we've got there is a very, very good approximation for the value of square root of 6.